Today on Building the Open Metaverse.
The insight that I evolved over time and that the change I made at Silicon Graphics was to identify the problems we're solving, figure out a useful interface, design systems, and then implement parts that were needed for the systems. And nothing pure about this. There's all kinds of cycles. It's a complicated process, but the cart behind the horse instead of out front substantially was sort of my story and SGI's story as we moved along.
Welcome to Building the Open Metaverse, where technology experts discuss how the community is building the open metaverse together. Hosted by Patrick Cozzi from Cesium and Marc Petit from Epic Games.
Hello, I am Marc Petit from Epic Games, and my co-host is Patrick Cozzi from Cesium. Hey Patrick, how are you today?
Hey Marc, I'm doing great. I'm very excited for today's guest. You may not know, but before we met, and even before Cesium, I spent about 8 years specializing in OpenGL and using it every day. So we have a very special guest.
Yeah, so today this is your show, Patrick, because our guests, we're super happy to welcome Kurt Akeley, a true pioneer in computer graphics, who led the definition of OpenGL, amongst other things, and we'll talk about his contribution to computer graphics. Kurt, we're so happy to have you with us. Welcome to the show.
Thank you very much. It's great to be here.
Kurt, thank you so much for joining us. We love to kick off every show asking our guests about their journey to the metaverse or their background. And for you, you've done so much amazing work at Stanford, working with Jim Clark and founding SGI. Tell us your story.
Okay, well, I guess, as far back as I can remember, I've been fascinated by understanding how things work and then wanting to develop my ability to affect how things work, to design things and build things and fix things. The tools behind are kind of a clue that hasn't changed. So by the time I was in high school, I was playing with TTL circuits and building circuit boards, and then college, I ended up doing a pretty substantial project with a guy who, the head of the EE department, who had been a vice president at Xerox previously, and together we built one of the world's first laser printers. Kind of repurposed telecopier, I think Xerox called it. And I did all the circuitry and, got all the mechanics of the xerography working, all this stuff. And so by the time I finished my undergraduate degree, I had a pretty good idea of how to do pretty significant system implementation. Found out I could get a PhD in engineering. I didn't know that till my undergraduate was almost done, like a philosophy degree in engineering. Who knew? But so I ended up going to Stanford and joining a PhD program there, and I was full of energy to find a professor to work with. There were 50 EE or 50 or so EE professors, and I couldn't find anybody who was building stuff. And I was just itching to build things. So during a seminar course early on in that first year, the course was being organized by a guy named Jim Clark, and then he got a speaker every week, and one week the speaker didn't show. So Jim got up and did a song and dance and talked about the amazing things he had done in terms of virtual reality, really, way, way, way long ago, and indicated he was looking for students interested in doing something interesting. And I just, I just about jumped out of my seat. And so I made an appointment, visited him in his office, and showed him the 600-page document that I had written and printed on that laser printer that was to describe the whole thing and how it worked, and he hired me as a research assistant for the next year as a result of that. And I spent the first few weeks of the following summer. He was nowhere to be found. He was busy developing this geometry engine, so I just went to the math science library and read Newman and Sproul and tried to learn something about computer graphics beyond the simple glyph kind of composition that the laser printer had required. So I had built that.
He was already working on the geometry engine at the time. That was really...
He was. And
can you tell people what the geometry engine was? Because I'm sure not.
Sure. Yeah, just reflecting, it's a critical part of what makes interactive computer graphics interesting is that you can define the objects in a coordinate system that's convenient for their definition, and then transform them into a coordinate system that is appropriate for rendering a display. And that mathematically that's straightforward, but at the time doing it fast was quite challenging. And so Jim took on that challenge. He knew that there was amazing work in integrated circuit development in a way that was accessible to mere mortals, And he knew quite a bit about that transformation process. So we thought he would try to take those two bodies of knowledge and use them together to invent a little computer circuit that would do those sorts of transformations. And he called that the geometry engine. He actually took 10 or 12 of them all together to do the job. But so they were geometry engines that collectively did that interactive transformation. Yeah.
So the ancestor of the GPU, the mother of all GPUs.
It probably is, right? And so I worked for him that summer and proposed a back end for this geometry engine to do some rasterization, and then he asked, kind of bumped, asked if I would be interested in starting a company with him. And crazy guy that I was, it turned out I was interested in doing that, which was kind of a disappointment to my parents and the people who had gotten into that Stanford PhD program. I took a leave of absence, and he and I and about 8 other people all collectively founded Silicon Graphics and off to the races. I did get a chance to finish that degree, actually, but that's a story maybe for later.
Yeah, that was a few years later, right?
Yeah.
Well, also, a word about SGI. I started my programming career on a personal Iris 4020.
Yep.
And I was supporting ILM at the time when they were working on Jurassic Park. I was at Softimage.
Excellent.
SGI at the time, in the early 90s, really transformed Hollywood. And there was even a cameo of the SGI file system in Jurassic Park.
Jurassic Park, I saw it.
That was crazy. And the impact that this company had on graphics in Hollywood through all of those 3D software and software like Flame has been nothing short of amazing. We forget.
Yeah.
Maybe we get to talk about the transition from SGI to NVIDIA and what happened there, but maybe not. So yeah, SGI was such a huge innovation leader. And we heard about Jim Clark in another episode when Ping Fu, who was overseeing his thesis on Netscape, he was involved in the Netscape endeavor with Mark Anderson.
I would actually argue that NVIDIA is what Silicon Graphics aimed to be. And in retrospect, what was SGI, Silicon Graphics, the SGI would better stand for systems graphics. I wouldn't argue that collectively and during that period of time, we systematized how to do interactive computer graphics on computing systems and solved a bunch of interesting problems and a whole bunch of things. But we never were successful at producing silicon to do interactive graphics, nor did we ever build a successful sort of high-performance compute combined with interactive graphics conglomerate that was the ultimate dream. And NVIDIA has done both of those things. So to me, NVIDIA is the Silicon Graphics as it evolved. And indeed, since I work in the Valley, right? And in some sense, I sort of think of us all as being employees of this Valley, and the companies are have functional reason. But in a sense, SGI evolved up through and became NVIDIA. And the success that Jim envisioned has actually happened. And actually a lot of the same people are there doing it. Right. So that's a short for how I feel about NVIDIA. Like it is what Silicon Graphics aimed to be. And SGI did a lot of really useful system level stuff, but we never got all the way to that end game.
So throughout your history and your career, you've been involved with all aspects of computer architecture. You've done hardware design, system software, you've written CAD tools, you worked on display technology, programming languages. We'll come back on NVIDIA and CG. So as you look back, is there any big takeaways? Do you have any favorite projects? Do you even have any regrets on all of those things?
I think I could describe my first 10 to 15 years at Silicon Graphics as this pathway from working on very, very low level things, thinking I'm going to be designing integrated circuits and studying for that at Stanford, and then actually doing TTL board level designs, and then ultimately moving up through that to ASIC design, gate arrays, not field programmable gate arrays, but the original gate array stuff, and then ultimately APIs for the systems. And I just think that the insight was that we were doing things backward when we started at SGI. We were doing things in the order I just specified. figure out what's a geometry engine, figure out how to put geometry engines together into a system and what other pieces we needed, and then figure out how that system ought to be interacted with by people who are using it, and then try to find what problems could be solved with it. And I think the insight that I evolved over time, and that the change I made at Silicon Graphics was as much as possible reverse that, to identify the problems we're solving, figure out a useful interface, design systems, and then implement parts that were needed for those systems. And you have experience with this. There's nothing pure about this. There's all kinds of cycles. It's a complicated process, but just in the aggregate, trying to get the cart behind the horse instead of out front substantially was sort of my story and SGI's story as we moved along. And I think that had a lot to do with how we got where we were able to get, which was, as you observed, pretty significant place by the mid-1990s. So get things in the right order is one. And then, one of those pieces of that order is what I call API or interface. But the other insight about all this was that ultimately it isn't just an interface. It needs to be thought about in a very special way. And there are names for those ways. And we can get to that.
So, Kurt, that's a nice segue in, because I've been dying, of course, to ask you about OpenGL and your thoughts there on APIs versus architectures. Before we jump in, though, so for those of us who are maybe not listening but watching on YouTube, you have one of the coolest backgrounds I've ever seen on a Zoom call. Would you be open to sharing that with the group?
Sure. It's just we built this house, finished last year, and it has this room in it, which is my workshop room, and I'm an engineer, and I love tools. I love using tools and understanding how to use tools and having tools, all these things. And so what you're seeing in the background is just one of many pegboards and collections of tools. There's far more out in the garage, but it's cold out in the garage. So these are the ones that are useful for doing indoor work that doesn't generate too much sawdust, and the heavy equipment and the like are out in the garage, which is occupied mostly by my stuff and not by vehicles.
So what is the latest thing you've built?
The latest, I guess the last thing was putting trim around the shelves that I put up in the master bedroom. For this house, a lot of things that my wife identifies things that are needed. The arbors out in the gardens that are all, made out of nice redwood and finished much better than usual outdoor things are, because I just like having the time and ability to do things slowly and well. That's a delightful aspect of being retired. Although I would say even in my professional career, to a substantial extent, I took my time and did things slowly and well.
So, Kurt, let's jump into OpenGL, right? So, in 1992, OpenGL allowed programmers to do legit cross-platform 3D, which created a tremendous impact. Before we jump into that impact, though, let's talk about a topic that's near and dear to your heart, which is the computer architecture. What is it? What isn't it? And why is OpenGL an architecture?
Okay, well, let me start with kind of the story of how we got to OpenGL. I'm trying not to get too long, and then you may have to remind me to get back to answer the question, because I could get lost. But the net was, Jim Clark had really good instincts, and he and a small team developed this IrisGL, which was basically an interface to the computer graphics systems that we were building in those early years at SGI. But what became clear over time, as we licensed it to IBM to use, and as we tried to port it from one of our machines to another, was that it really wasn't a very well-defined interface, that we found ourselves doing experiments to try to figure out, gee, if you do this and that, what happens? And we would do the experiments on the old machine and then try to make the new machine work like that. And that's not a very disciplined or thoughtful way to go about things. And then you license it to someone else, and they're trying to make it. It just gets to be a mess. So from an implementation standpoint, it was an inadequate specification, and from a porting standpoint, for people using IrisGL, it was difficult to write a program that would easily run on a different platform than the one that it was developed on. And it turns out these are classic problems, right? These problems were identified and addressed and substantially understood and solved by Fred Brooks and the team that designed, conceived, and implemented the IBM 360 back in the early 1960s. I think it was introduced at the World's Fair in New York in 1964, and I happened to be there actually, but not at the, I didn't have any idea what was going on. I was 6 years old, but the net is it was a long time ago and it had been sorted out. So what we really needed for our graphic systems, what the industry needed was an interface that had these kind of disciplines about it that Fred had figured out. The name for such an interface is an architecture. IBM 360, that architecture is an instruction set architecture, but it needn't be an instruction set. And they give in the book that Fred and Garrett wrote, years later, they describe the architecture and implementation of a clock, for heaven's sakes, right? I mean, anything can be thought of in this way, and it turns out graphics. So, I mean, sort of to my embarrassment, because I knew when Fred Brooks at the time, I didn't know about this work, and we kind of refigured it all out with using different words and different names, which is not a great thing, but what we were doing is solving the same problem with the same approaches as Fred Brooks had. And now there's other aspects to that story. I guess the other thing is other people solve these problems as well, and the X community, the X Windows Systems community, was moving ahead with a standard that evolved an old graphic standard, Programmer's Hierarchical Interface for FIGS. I'm not sure exactly what it stands for. Sort of using that as a motivation, we're coming up with a thing called the FIGS extension to X, or PEX. And I was aware of this at SGI, and we thought that this was kind of a disaster is perhaps too strong a word, but a substantially less optimal result if the world ended up using that for a whole bunch of reasons. But one of them, not to be discounted, was that even at that time, we're talking early 90s, the X Windows system ran on maybe 1% of the computers that people used. The other 99% were PCs or, whatever else. And yet this standard was being implemented in a way that was going to be linked only to those X Windows Systems computers, which just looked like it from a standpoint of overall industry, not a wise move. So we, led by me, but we at Silicon Graphics set out to do a standard, really an architectural standard that would be better for us, and we thought better for the industry. Longish answer, but that's some of the history for how we found ourselves doing a standard.
Yeah, look, that's really awesome. And talking about that impact on industry, if we look at it from the perspective of the end user, and how would you describe the impact of OpenGL for folks working with interactive content, whether it's CAD or an animator or visual effects? Like, how did it impact, how they worked and their workflows?
It's more of a business change than a technical change. I mean, most of the things that OpenGL had when it started, all of them were available in IrisGL and available in the HP interfaces, right? It's just that those things weren't really available outside that 1% of computers that ran the X interface, or X Windows system, and they were expensive. So what happens when an architecture like OpenGL is a contract. It's a contract between people who implement some mechanism and people who use those mechanisms. And the contract has a lot of nice properties. And the net result is that it creates a marketplace, or it wildly accelerates a marketplace that otherwise struggles because it doesn't have the portability, because it doesn't have the reliability, because the interface didn't allow the right kind of cleverness underneath for implementers, or it didn't allow portability for use. All kinds of bad things happen when those interfaces aren't good. By creating that interface, by having that contract, it allows investment to happen. It allows, at all levels, money, people's time. It allows multiplicative goodnesses to happen. And so the net result is that started spitting the 3D model of an airplane on the GT. And that was like the first time any of us had seen such a thing, right? So sure, some ENS system or flight simulator had done something like that in the past, but literally nobody saw those. That the SGI machines and all, an interesting number of people did, but by creating this marketplace with our architectural standards, in some sense, everyone. I mean, your mobile phone does it just fine now. In fact, far, far, far better than any of those expensive things did then. And I think that's So that's the difference. It isn't that it was the first time it ever happened, but it became ubiquitous that these sorts of interactive experience with computers could happen. Yeah.
So, but you characterize it as a business decision, but at that time, Silicon Graphics was the clear leader in graphics, and you somewhat enabled competition. So, was that a hard decision?
Yeah. Well, I mean, Jim wasn't happy with me about it, and so it's a tough call. I think the trade-off, the way I saw it at the time, was if we stick to proprietary, we're going to be going it alone, and worse, we'll be forced to adopt the things that other people put out there as standards, and that's going to compromise our ability to do what we want to do. So it's you don't get to replay these things. I'm sure some B school person could do a bunch of studies across it, but I was happy at the time that by creating the standard, we were able to move ahead as a company and keep doing the things that we wanted to do. And I don't know, I didn't join Jim Clark because I was a cutthroat, clever business kind of a guy. I wasn't, and I'm not, right? I'm a technologist. And so it was a relatively easy decision for me to open expand the tent and bring people in and have it become a standard. But I think Jim did have a clearer understanding, and I think it's quite possible, Mark, that SGI would have, maybe lasted a little bit longer in the 90s as a force if we had kept things proprietary. I don't know, but we didn't.
I suspect you. I do suspect you were right that history, in hindsight, is on your side. Actually, you revived a painful memory because when SGI licensed the technology to IBM and created the RS6000, which was a monster, a non-functional monster, I was on the team at TDI in charge of porting Explorer to the RS6000. It would not work.
Wow.
And that's how I found myself at Softimage, because I could not deal.
Well, I apologize, because part of the problem was that it was impossible to port IRIS-G successfully. So there you go. All right. I've never had confirmation this way.
Let's stay on the topic of open standards, because, it's one of the things we do on that show. And Patrick and I are actively involved in the standardization effort around the metaverse and starting, trying to get the industry to agree on ways that we could represent interactive content, just like HTML, was representation of the hypertext. And, the same for virtual worlds and working around USD and GLTF. I know you've been working with the Chronos group, and Neil has been on the show a few times.
Yeah.
And we're partnering with Neil at the Metaverse Standard Forum. So this is all the same family. So do you have advice for us as we set up to develop, to try to standardize something even bigger than just the graphics component, which is that metaverse and those fully simulated worlds? So how should we go?
I can reflect a little bit from my experience, and I'm not sure if it maps well or not, but one thing is, remember, I was at SGI, and SGI was a dominant force. And so we had a real advantage. And so my experience with how to go about this is a little biased or distorted by that, because we could invite people to join us, and they did, and if our business didn't matter, or if the work we had, so I had that advantage. But I early on, I really set out to sort of earn the continued trust of all of the people and the companies who were involved. And we did that by being absolutely scrupulous about not taking advantage of our position of strength in the group and in the market, by building a culture of sort of voting and appropriate behavior of not doing nasty IP kind of things, which the world has learned a whole lot more about the sort of bad things can happen. And SGI, at least, I don't believe did any of that. In fact, we actually indemnified people against patent infringement in the OpenGL license, which is a crazy, crazy thing to do. I can't believe that happened. But so building that trust among the participants, and then also arranging things so that the people participating in evolving standards are the right people, and how do you say, like, you want to build an organization that attracts the really good engineers, where they feel like their ideas will get a good hearing and things will be done, and not just tabled or crunched. And they're a little like political. One of the things that we did, for example, is there was a whole lot of obvious stress about conformance testing. If you're going to have an architecture and you want to make promises in a contractual way, you better be testing those promises. But boy, what an opportunity to injure your competition by putting things into tests that are preferential or whatever. Like, it's obviously a set of a minefield. And so one of the things we did is we split the working committees for that kind of thing to be separate from the committees that were evolving and defining the standards. Like, let's not stir all this together in one pot. Let's so you can take little steps like this organizationally to keep that trust and keep attracting the kind of people that you want to have be involved. I think OpenGL got off to a really good start that way. I'm so pleased with the way the extension things went, for example, that we saw the Windows system had an extension mechanism, but it turned out it had a nearly fatal flaw. The X extensions were defined against only the core, not against the other extensions. And so you end up with a kind of a center core with a bunch of little pieces stuck on it, and not an evolving architecture. And we really wanted the evolving architecture, so we just made some simple rules. And then we'll index the extensions starting at 1, and when you write one, you've got to describe your stuff with respect to all the ones that have indexes lower than yours. It gets to be a big problem, and so later on the spec evolves, and then you sort of raise the playing field, and now you don't have to write against all the earlier. But the point is, we identified what we wanted, which was the evolving standard, and then we looked at what was out there and found the problems, and I think that there are, last I looked, over 400, I think, OpenGL extensions, and by no means is it perfect. You can hear plenty of horror stories about issues between extensions, but you wouldn't have 400 extensions if it didn't basically work, right? It would have ground to a halt decades ago, literally decades ago, and it didn't. So while, like all things, not perfect, but much better.
Patrick and I go through the Metaverse Standard Forum experience. And trust is by listening to everybody, and you have to go slow and spend a lot of time together, which is kind of against our nature as entrepreneurs, and we're going to get it done, and we are bred to go fast and have milestones and converge quickly. And here, that trust building exercise sometimes feels, it feels slow, but I think
that's right.
When you have a group that can actually openly debate the issues, then this is where the real progress starts. So
when I started working for the guy building that laser printer as an undergraduate, he hired me for a summer and set me down with all the work that had been done by others. And I just worked 8 hours a day and read and organized and figured out what everything was and gave everything a name. And then, but he was getting really nervous, right? I mean, I've had 2 or 3 weeks into this and nothing had happened. But then all of a sudden, boom, like when it's like, okay, here it is. This is how they all go together. This is what I'm going to do. And then when we're moving quickly, right? So it's just taking the time to make the tools, to make the jigs, to figure things out, to not, but just to be fair, quick prototyping and failing quickly is also really smart. So, and right? So it's just like, it isn't just from hardware to software to to product to customer. It's everything has cycles, and there's no pure answer. But boy, putting in the time to think things through. Write a glossary. If I write a paper, first thing I do is write a glossary. It doesn't matter to me if the glossary is going to end up in the final paper. That's not the point. The point is, I'm going to use vocabulary. I'm going to use words, and they should mean something, and I should know what they mean. And heaven forbid, they shouldn't mean multiple things that are kind of by convenience. Just a little bit of rigor about that goes a long way to clarity, and on and on.
So, Kurt, I wanted to ask you a bit about levels of abstraction, right?
Sure.
If we look at kind of the GPU architecture evolving over the years, then maybe the expectations of the end user in terms of, visual quality, visual fidelity, the complexities of the scene, and then also just wanting more and more people to be able to be 3D creators and 3D developers. When you think about the level of abstraction of OpenGL, or maybe a Vulkan, or even a game engine today that maybe you code against it or has no code visual, what do you think? What are the, and I'm sure it's more than one level, but what are the levels of abstractions that, that should make sense today?
I want to come to that, but I want to riff a little bit more just on levels of abstraction first. And again, you remind me if I don't get to the end. It's really, really central when you're defining an abstraction. Getting the level right is hugely important. And one of the ways to understand that is that, as you've strongly alluded to, there needn't be only one in the system. There's likely a stack of software or hardware or whatever, and so there's multiple levels of abstraction. The ones that I've most experience with are the lower ones. So, but even an architectural abstraction might not be the bottom, right? So certainly a microcoded machine has its own microarchitecture and another level of abstraction inside. But I've spent most of my career down at these low levels and not spend a lot of time thinking about or interacting at higher levels of abstraction, except to the extent that I need to understand what's needed up there to do the right things down lower. One thing that is an interesting, I think, fact about the right level of abstraction for interactive graphics sort of toward the bottom is that I think OpenGL hit it pretty well. Again, riffing off what Jim and the team had done with IrisGL. But we stuck to our guns and didn't move it way up as some people were really lobbying for us to do. But also, it ended up being higher than what made sense 20 years later. And indeed, it is higher than what makes sense 20 years later. It needed to, remember, it's a contract between implementers and users. The implementations for interactive 3D graphics were a pretty mixed bag back then. And parallelism hadn't really even been exercised in very many interesting ways. And memory systems were very bespoke at that point. You had a texture memory, you had a frame buffer. I mean, they were different things. And so the interface needed to be higher in order to have enough room to A, abstract away what had to be beneath, and B, leave enough room underneath for implementers to be able to figure out, evolve, and experiment and try things and find what eventually became the more or less standard way of doing these things with these massively parallel cores and sharing the cores amongst the different pipeline stages of the engine. I mean, that was not obvious 30 years ago. At least it wasn't obvious to me. But OpenGL interface was on a high enough abstraction to do that, and yet low enough that it could be imperative rather than declarative. And an imperative interface is absolutely critical for something you're going to call an architecture. People have to be able to build things and make things, use it in a functional way, and not just give it directives. So it was low enough to be imperative, but high enough to allow all that experimentation. And frankly, now 30 years later, the implementation space has matured dramatically, and it's pretty clear what to do down there. And so interfaces like Vulkan, harkening back to Kronos, right, make a great deal of sense because they accomplish, by lowering the interface, they give greater control over the mechanisms that are there, and they also broaden the base, so they can make compute and graphics all work off a single interface, which OpenGL really would have been a pretty tough. I mean, people did GPU work, a lot of good work on OpenGL, but it just isn't the right interface long term for doing compute things. So it's because of the maturity of the implementation space, interface moves down, becomes broader, and gives yet more access. Much easier to write a game engine on top of a Vulkan that isn't itself trying to manage resources. I mean, it's kind of the worst thing you can have is to have multiple layers in the same stack competing to manage resources. OpenGL had to, because the definition of those resources is just so needed to be very specialized and managed that way. But again, Vulkan needn't do that in the same ways because that definition. So that's kind of a longish discussion of thinking about levels of abstraction. I could go on and on, unfortunately, but I want to come back because I think you asked about what are the appropriate levels of abstraction moving forward. So I guess to answer that, I would say that things like Vulkan are, I think, a wonderful level of abstraction for the architectural level to specify the hardware. I have almost no experience with the levels of abstraction above that. I've never written code for a game engine. I've probably used them without knowing that I was using them in something. But I love the fact that, OpenGL is kind of this awkward middle ground. By moving down to Vulkan, then you can have the next level, do the resource management, and be a somewhat more descriptive kind of interface that's more about defining data structures and then having things done to those data structures. That's almost certainly a more appropriate level for most people to do graphics, right? I always used to say OpenGL, thoughtfully designed, but it's a power tool, right? You can cut yourself really easily. I think Vulkan, all more so, right? Very few people should write Vulkan programs, but because it's a great foundational abstraction, very few people will need to write Vulkan programs. There's game engines, almost everyone who uses interactive graphics will be either coding to a game engine or running on something that was coded to a game engine, and that's all wonderful. But what are the right interfaces for more virtual reality kind of things? I honestly have no opinion about that.
So do you think Vulkan had the success it deserves? Because, we have Metal, we have Direct 3D. I think we have a little bit more fragmentation today, more fragmentation than ever, actually.
Platform companies like to own APIs and like to own the interfaces on their platforms. And so my understanding is that Apple has succeeded in making it almost impossible to make Vulkan run. Maybe Microsoft hasn't gone to that extreme. It's funny how the tides come in and out on on these kinds of behaviors. But so I don't know what it should have. I could just say that there are powerful business contingencies that cause Apple to do what Apple does and Microsoft to do what Microsoft does. And I'm just so pleased that Neil and the team keep up the good fight and do their best to make it possible to write things that run across. But that it'll work. It's far be it for me. So if I could change that or have strong opinions about what these companies do.
Over the past few years, ray tracing has been an amazing development in the world of GPU with, the 2 layers of acceleration, one, the silicon and the RTX interfaces, and the other one, which is the AI layer. Where do we go? Can we ever have a real-time path tracer, a proper real-time path tracer? Do you think we can get there with that?
From an implementation standpoint, I'll tell a short story and then trying to come back to it. One of my first professional talks was at the graphics hardware conference in Europe. I don't know, it's like 93 or I forget 95 maybe, a long time ago. And I part of my pitch was to say that this voxelization stuff, that building hardware to do voxel rendering is crazy, that we should just use standard graphics hardware and texture maps to hold the voxels and render planes. This is a straightforward way to do volume rendering. And of course, turned out I didn't have any idea, but Ari Kaufman and his students were in the audience there, the audience of 30 people or whatever, I thought. So I was definitely preaching heresy to the choir. So the funny thing about that, though, is I just revealing, this is how I think, that I like where NVIDIA has gone with ray tracing, implementing it as part and parcel of circuits that are also very, very capable of doing sort of forward projection graphics. And the business reason for that is you just never want to leave anyone behind. You want to keep everybody in the tent and add more stuff. But from a technical standpoint, and you can think of path tracing or ray tracing as it's just sort of a texture mapping function call from a shader. I don't know how exactly they reveal it, but it's certainly possible to do that. And if you kind of embed it at that level, then one doesn't need to make this sort of all or nothing kind of thing that path tracing versus forward rendering tends to do. Rasterization instead would say, no, it's like, yes, the answer is yes. We'll have this, we'll have that. All those early ray tracing papers, usually there was only one bounce, the interactive, they're interactive, but all they're doing is sort of an awkward kind of rasterization. But over time, you get more and more performance, more and more capability, more and more research, and successfully figure out how to get these acceleration structures to actually themselves interactively updatable. And I'd seen that was a big problem not too many years ago. Maybe that's been addressed well as well, and then you can put all this together into really attractive things where you ray trace where you need to ray trace, and you forward render where you want to forward render. If you're designing headlights for cars, you want perfect ray tracing. But if you're an artist, you want a system that has the knobs that you know how to use and that do the things you want to do. And those knobs have evolved over forward rendering, and they're well implemented there. And it's like, so at best, there'll be a long transition. I just think, architect the interfaces so that they support that transition instead of forcing it to be separated. And I think that's what's happening. So
another topic is cloud and the edge, with the promise of a 5G low latency network. So what can the cloud and the edge, what kind of role can they play in interactive graphics?
Well, it's interesting. I mean, I don't know. Maybe someone did it before SGI, but we were doing reality servers back in the 90s. So like it wasn't called a cloud then, and it wasn't in the sense of a modern Google data warehouse or something, but it was the same kind of idea. And I thought I'd use this as an example to bring up another architectural important little observation, which I've learned at Stanford really. And that is that, compute, it's nearly free and getting freer, if you will. And the architectural challenge always is about data, having the data you need, where you need it, when you need it, which often involves moving it around or making multiple copies or whatever. And so, this question of, do you do compute in the cloud, or do you do compute at the edge, or do you do compute on the handheld device, which I don't know if that's what you mean by edge, but it's like at Google, the sort of the edge of the cloud system. But whenever, where do you do it? That has less to do with where the compute is expensive and more to do with the data, where the data is expensive to have, how much data has to be moved. One of the jokes I would tell people is that back when I started doing computer graphics, there would be this handful of polygons, a teeny amount of data, and a 3D graphics pipeline exploded it into 1,000 by 1,000 pixels. And nowadays, there's this terabytes, perhaps more, of data, and a graphics pipeline collectively collapses it down into just a few thousand by a few thousand pixels, right? It's like the number of pixels stayed almost the same, but what happened is the amount of data behind it is just growing exponentially, insanely. And so from an architecture standpoint, the decisions one should make is where are the data, where should the data be, and what's expensive. And cloud rendering makes sense if you're rendering huge data sets and all you're delivering is just simple things like images, right? And so that makes sense to me, and it's consistent with the way things. I mean, if you're Boeing and you're designing an aircraft, I don't know the numbers, but I can tell you they're big, right? The number of bytes to describe a modern jet aircraft is just insanely large, and they're valuable, by the way. And they don't want. I was going to say they don't want McDonnell Douglas to have, but they bought McDonnell Douglas, so they don't want Airbus to have, right? So it's nicer to keep them in a safe place and just do these really, really small reductions of them into graphical images rather than trying to move the data all out of these unsafe edge places. So, that was the SGI thinking there. It all makes sense to me that there'll be more compute where the data are. And so then maybe for a game, it's easy to have the data be local. Probably not, though. I mean, I know nothing about modern game programming, but if it were, then you should do the rendering locally. But if the data is huge, or that maybe not.
Yeah, you have the multiplayer problem, and
yes,
the network layer seems to be a bigger problem for scale than the graphics layer at this point. The synchronization.
Yeah, I never like Zida did a whole lot of work with that. Decades ago, right? When he was working on military systems, I think, and he's been teaching this for a while. So yeah. I mean, the multiplayer, where's the data? All these are more important in a lot of sense than where is the compute cheap, because compute just is cheap.
This is fascinating, Kurt. We could talk about those things forever.
Yes.
One thing we'd like to do is, advice for people wanting to enter graphics right now.
I mentioned that when I started working with Jim, I went to the math science library, and I read Newman and Sproul, which was kind of the Foley and Van Dam alternate back then, and that's how I learned a bit. And then I did stuff. So I would just say, doing things, it's unbelievable. I mean, I sit here and program still, and what you can learn by just going out to the internet and asking, and how quickly you can make something work, and how much you learn by just banging through it and making something work. It's just, so if you want to be able to do graphics, right? There's that simplicity. Reading, I would suggest two things. One, which both of them have a teeny self-serving aspect, but I really share them in I think with the right spirit. One of them is, when I want to understand how something works in graphics, how does environment mapping work? Then because it wasn't part of OpenGL when I did. Well, it turns out that there's an OpenGL extension for environment mapping, and if you go and read that extension, it's remarkably powerful document. And one reason it's powerful, because it basically says, here's how the extension works. Yeah, okay. Well, but the great thing about those extensions, and by the way, I didn't do this, people did it later, is they put in a kind of a history set. What were the issues that we ran into? And they said, we did this when we were developing the early extensions, but then I threw that stuff away. Hey, mistake, right? It is so powerful over time to have that history. What are the things we considered? What did we decide, and why? And by reading through that history, you learn so much about environment mapping, or 3D texture, whatever it is that you're studying. It's a very, very rich source that's available on the open source history, and I think it's almost certainly underused in that regard. It's great stuff. And then finally, in terms of reading books, I'll put this one up. My name's on here. I actually wrote a chapter in this. That's not the point. The point is, John Spike Hughes, his name is on there because he wrote somewhat over half of the book.
The title of the book, for those who do not have the video?
Computer Graphics, Principles and Practice, 3rd edition.
Yeah, even if people are bound to use game engines, I mean, you're so much faster if you understand the underlying mechanism. So you don't actually need to learn those level stuff, but I think understanding it gives you so much insight, and you'll be much better using a game engine if you understand those concepts.
Mark, so the book, Computer Graphics Principles and Practices, Morgan McGuire is also one of the co-authors, right. and Morgan was on one of the first episodes of the podcast.
Yeah. A lot of great people. But Spike he wrote so much of it.
I remember waiting in line at SIGGRAPH. Many of you signed the book for me, which was very cool. I'm still working my way through it, though. It is a thick book.
Yeah, it's a tome.
Okay, well, Kurt, we wanted to wrap up. I kind of had two things. One, I wanted to share a quick story with you. So we talked a lot about OpenGL, and you also just mentioned recently, hey, going online just in general and getting questions answered quickly. I spent a lot of time on OpenGL.org, the forums back in the 2000s, and I met someone there named Christoph Rico, and then we met in person at SIGGRAPH. Hit it off really well, and then we decided that we wanted to do a gem-style OpenGL book to get a bunch of different authors together. And we went and did that. And we had maybe 40 or so different contributors who either wrote chapters or reviewed the book OpenGL Insights, which I have on the video here. Not trying to plug it. We make almost no money from royalties. But I want to say what I learned was like the amazing intelligence and passion of everyone that was building with OpenGL. So I'd say, not only is it an architecture, as you say, not only did it enable, an ecosystem in the industry, but the community that it built, the people, and how just passionate and how much they just loved it, and how the OpenGL BOF at SIGGRAPH was like the event of the year for all of us. Yeah. It was very, very cool.
No, it was really a true catalyst for a community, and that community is what we build the metaverse to.
Yeah.
We build the metaverse upon the work of that community. So it's such a foundational role that it has had. So
wonderful time. And it was, we worked hard to make that community. So it's wonderful that it happened and that it continues to happen.
And then, Kurt, our tradition for wrapping up the episodes is if you'd like to give a shout out to any person or organization.
Yeah, I just want to give that shout out to Jim Clark. In the end, Jim, he had the bravery and he had the drive to create a company, and he created an opportunity for so many of us, but in particular for me, to use that to satisfy my desire to build things and understand things and develop things, but ultimately to build the community that you just are describing. And for me, it all traces back to Jim and his inclusive way. You know, whenever we had an event in those early days, he'd jump up and introduce all the founders, and just he started that sense of family amongst the set of us that created Silicon Graphics. I think Silicon Graphics have that sense of family. I think OpenGL has that sense of extended community and family, and it's what makes it all worthwhile to do this. So I really appreciate that from Jim.
Well, thank you, Kurt. It's been fantastic to have you. A little bit of a trip down memory lane. I mean, everything all of this insight, you know, it also explains why we are where we are today in terms not only of technology, but also of mindset. And I think it's important.
Yeah,
I think we're going through an unprecedented level of collaboration in the industry. And I think, you know, that we owe that to going to SIGGRAPH and you know, seeing and going all of that camaraderie and that, you know, the importance of working together and being open. So I think we're fortunate that people like you studied all of that, like you and Jim Clark. So thank you very much for being there with us. It's been a great moment.
Yeah. Well, thanks again for having me, and thanks for being those people who keep the flame lighted.
Yeah, we try. And thank you to our audience. We're delighted to hear from you, to have your feedback. And until the next episode, thank you very much.